by Chahan Kropf, who couldn't actually be here because he's happily skiing in the Swiss Alps, I guess. So the work is about a new module which we implemented in CLIMADA. CLIMADA is a modeling platform for impact assessment developed by the Weather and Climate Risk Group at ETH. And this new module is meant to carry out uncertainty and sensitivity analysis of any impact model that we can develop within CLIMADA. Do you see my next slide? Yes, okay, good. Yes. So yeah, what is CLIMADA? CLIMADA is an open source probabilistic risk modeling platform for impact assessment and adaptation option appraisal. It's open source, written in Python and available on GitHub at the link in the bottom. It basically follows the classic framework for impact modeling, so hazard, vulnerability, and exposure. And this new feature, which we called UNSEQA, uncertainty and sensitivity quantification, basically fully integrates CLIMADA and enable the performing uncertainty sensitivity analysis with any impact model which is developed in CLIMADA, so tropical cyclone, floods, European windstorm, and et cetera, et cetera. The framework of our modeling setup, it follows the standard framework for carrying out sensitivity analysis. You sample input factors from the hazard, exposure, impact function, and measure. Then you propagate them through an uncertainty analysis, Monte Carlo kind of analysis, and then you finally visualize the sensitivity indexes. We applied this on an existing paper and perturbed the input factors of exposure, hazard, and impact functions. So just very briefly, the original values in the paper are the dotted lines that you see here, whereas what we get from the uncertainty analysis are, of course, the distributions. And we interestingly see that if, for instance, things can change substantially when we relax the assumptions about the input factors. And interestingly, we see that there is a bimodal distribution, for instance, in the average annual impact of the number in terms of the number of people affected. And in terms of sensitivity analysis, we can actually display what input factors matter the most in a geographical spatial setting. And we can also see that across different return periods, actually, the importance of input factors for the output of interest differs. Thank you very much.
Thank you. Then let's move to the second presentation in this breakout room, which is by Carlo Giupponi. We cannot hear you. Is your microphone working? We cannot hear you.
Let me check.
Oh, now it works.
Can you hear me now?
Yes.
Okay, sorry about that. And can you see the screen too?
Yes.
Okay, wonderful. Okay, so this study is about climate proofing of economic activity. So we analyze risks in a case study in the Italian Dolomites. We studied then the Alpine region, which is characterized by very high temperature rise in the last decades, which generated a lot of consequences for the environment and for societies. An emblematic case has been the Vaia storm in 2018, with damages in this northeastern part of Italy up to 2.5 billion euros. So in this study, we wanted really to provide some information useful for local stakeholders. And therefore, we tailored our studies, our activities for economic sectors: summer tourism, eyewear industry, electricity distribution, and winter sports and events. We applied a method that we developed in a previous European project called culture risk. And what we did in particular here was to focus on extreme events with the return time of 100 years. I will go fast through these slides, and of course I will return back to them in the discussion later. So, as quite often is the case, we analyze the risk as a function of hazard, exposure, and vulnerability. In this case, in particular, we focused on expected damages of exposed assets of those four sectors with these events. And what is peculiar is that we applied this general framework with quite specific climate modeling and downscaling, with the socio-economic spatial analysis, and also with monetary valuation of the expected damages. In particular, for example, for climatic variables, we do not look at temperature, but we look, for example, at the variation in wet snow events that may be quite dangerous for electricity network. We apply multi-criteria analysis for aggregating multiple indicators, in particular for vulnerability, and we tailor the general approach to the four sectors. Having done so, and having various sources of uncertainty, we generated many maps for each of these different risks. And importantly, what we did was not only to generate all these average, so to say, maps, but also to communicate stakeholders, in particular, the changes that we expect as compared to the historical situation, and the uncertainty that are associated to our estimations for the future. So, in conclusion, very briefly, we found that tailoring these climatic hazard indicators allowed to bridge, in fact, to bridge the needs of local economic agents with the outputs of climatic models. The focusing on a climatic scenario only without looking at the future economic scenarios provides stakeholders with simple and clear messages, which are directly related with their current experiences. The tailoring of economic sectors, of course, is directly related to the needs of economic agents and investors, while the multi-risk map that you see in front of you at the moment provides instead a synthesis that can be useful for local administration. And of course, these maps can then be the basis for further studies, in particular to zoom into specific areas that could be of greater interest. Thank you for your attention, and of course, I'm available for any discussion later.
Thank you for your presentation. And we move now to the presentation in the second room, modeling human-water interactions. And the first speaker is Maurizio Mazzoleni.
Yes, hi. Can you see my slides?
Yes.
Yeah, great. So good afternoon. Well, my name is Maurizio Mazzoleni, and today I will briefly show you a new research activity that we actually recently started within the ICISC European project. So climate services have been used since many years already by different user communities and institutional actors to retrieve useful information about physical variables, like, for example, water level or precipitation. And they can be used for different purposes, like water management purposes or flood forecasting. So what we want to explore, so the main research objective behind these research activities is to explore how can we integrate end users' knowledge that is actually not included in climate services. So how can we include it in climate services in order to better understand the complex dynamics between human and climate, and so avoiding future unintended consequences when future adaptation actions are adopted. So to do so, we are basically, the first step is to understand the bidirectional feedbacks between adaptation actions and different type of hazards. They can be floods or droughts or, for example, heat waves, and the dynamics between different sectors. We will focus also on different spatial scales. For example, we'll see how upstream adaptation actions can indeed affect downstream communities, and how adaptation actions that are implemented using short to medium term forecasting can have an influence, so an unintended consequences on the longer terms in terms of temporal dynamics. And this will be done by using two different approaches, two complementary approaches. So from the one end, we'll use system dynamics, and for the other end, agent-based model, in order to complement the pros and cons of each one of these approach. The model that will be developed will be actually applied in 6 living labs in Europe and 1 living lab in Namibia. So we call it living labs because we are going to develop the model together with the stakeholders. So it is a co-production process with all the stakeholders. And we are not only going to develop them in our offices. So the idea is also to understand, to discuss with the stakeholders if the dynamics that we are identifying are actually correct, or if we can, what we can improve. So the expected results of this activity will be a set of models that will empower these end users to better assess future trajectory of adaptation actions and plan a climate neutral future, and also better understanding the complex dynamics between climate change, climate services, and adaptation actions. This, of course, is part of this research is part of PhD research of Lotte and Riccardo, that they recently started a PhD at Freie Universität and Uppsala. So I'm sure you will see their interesting work in the upcoming workshops and conferences. And of course, I'm open for any question about these new activities, and thank you.
Thank you for staying in time. And the next presentation is by Andreas Paul Zischg.
Thank you, Jürgen, for the invitation. My name is Andreas Zischg. I'm professor for human environmental system modeling at the University of Bern in Switzerland. And I'm focusing on analyzing and modeling flood risk change. If you are doing a flood risk analysis, that's a simple step. So you are coupling different models, climate models, hydrological models, and hydraulic models to generate flood maps. And these are spatially overlaid with elements at risk and the vulnerability. So that's common sense. However, that's only a tiny snapshot in time and space. So if you are wanting to know how flood risk is changing, how the rate of change is for a specific area, so you have to look at flood risk change, because all the drivers of change or the factors of risk are changing, but they are not independent from each other, so they influence each other. So you encounter some features of complex systems, features of complexity, as for example numerosity, interdependency, hierarchy. We are working on multiple scales. You can find feedback effects, nonlinearity, history, path dependency, time lags, and the emergence of spatial and temporal patterns. So these features of complexity must be considered, and to allow the model to consider this complexity, we have to implement the ability to model structural change of the processes and the decisions rules behind, and adaptive behavior. And in the last few years, we did a lot of feasibility studies on how to do that. And I can state that by coupling different specialized models together with a model coupler in a couplet component modeling, that's offers promising opportunities to model these features of complexity, or at least to consider them in the modeling. So in case of any question remained, so I will be there in the discussion later. Thanks.
Thanks for the presentation. And then the next speaker is Jiaqi Ge. Is the speaker here? Clearly? Maybe not. Then we move on to the next room, modeling impacts in the transition to a green economy. And here the speaker is Jiaqi Ge.
Hi, I will share my screen. So just 1 sec. Can you see it? Sorry.
Yes, I can see. You have to use the presentation mode.
Okay. Yes.
Now
Okay.
it's working.
Okay. So thank you for having me here. My name is Jiaqi, and this is work with my in collaboration with my colleague Dr. Furtado from IPEA in Brazil, and we want to model the urban transition from a conventional to a green economy. Sorry. Just 1 sec. So the motivation for this study is an escalated transition away from traditional fossil fuel-based economy to a green or knowledge-based one amid increasing climate change concerns, especially after conferences like COP26 last year. Countries like Norway that used to be very heavily rely on the oil and gas sectors, they're committed to phasing out the oil industry and diversifying its economy. And also many cities that has a large proportion of employment in traditional sectors, they also need to adapt quickly. And historically, as we have seen repeatedly, that the transition from the old to the new economy is not always smooth. So what we want to argue here is that the path to the great economy is can be quite unequal, and we've already seen that in previous waves of industrial revolution and globalization, there have been winners and losers created in this process. For example, in the UK, you have the North-South divide, where the South is more successful in transitioning into a knowledge-based economy, and the North is kind of losing out in the phasing out of the traditional mining and manufacturing industries. And the same can be found in many countries in all over the world, in both developed and developing or emerging economies. So we argue that while successful transition to the green economy can take many forms, unsuccessful ones will have devastating social consequences. And I think we've already noticed some of them in different cases. And these consequences could be long-term unemployment and homelessness in cities, high crime rates in cities, and also extreme social divide and polarization, as we've already noticed. So in this study, we proposed a stylized agent-based model of urban transition, and we want to simulate the transition path of an urban area from traditional economy towards a green one. And importantly, we want to explicitly simulate and couple two important markets in an urban area, which is the labor and the housing market, and introduce feedbacks between them. And also, we want to focus on the time scale of medium term, which is approximately 10 to 20 years, because we feel like this is there's a gap in currently in the urban modeling research, where a lot of research have been focusing either on the very short time scale, in, for example, transport modeling or pedestrian modeling that looks at by days or even by minutes, or like a lot of economic studies, which focusing on the different equilibrium status, which focus on the very long term, as the economists like to say, like in the long run we're all dead. So I think in the medium run is somewhere as it has been lacking, and also I think the transition path can be quite important, not just the outcomes. And this is also, this will also have important implications for policy. Thank you.
Thank you. Then the next presenter is Corey Lesk.
Hello. Thanks so much for having me. I want to talk to you a bit about mitigation.
Can you use presentation mode?
Yes, sorry. There it is.
Thank you.
So what I'm going to talk to you a bit about is the mitigation and adaptation emissions that are embedded in the broader climate transition. And by broader climate transition, I mean everything we need to do to arrive at a reasonable climate future, including avoiding climate change by deploying renewables capacity and adapting to the impacts of climate change we've already caused, including things like retreating from coastlines, protecting perhaps some other coastlines, and increasing space cooling as the climate warms up. And all of these interventions require energy to deploy and get going. And in the short term to medium term, that energy is coming from fossil fuels. So this is what I'm calling embedded transition emissions. There are emissions that will necessarily happen just to get the mitigation and adaptation going. And I think that these are a complex climate risk for a few reasons. First, fossil fuel combustion to power the transition eats up remaining carbon budget, leaving less space for the rest of the economy. It also could cause potential transition warming feedbacks. And all of these things depend on decisions taken by people in that transition. And I argue that these things are not presently accounted for in most research or in the IPCC or policy. So the question from this is, how much CO2 emissions are embedded in this transition? And this means, are they big enough to be a risk? These emissions are important. For a 2-degree Celsius transition, they total close to 100 gigatons of CO2 through 2100. It's around 3 years of current global emissions. And you might be saying, well, I don't know if that's really big or small. And I think one way to conceive of that is to compare a slower transition than this versus a rapid transition. And the picture there is that a slow transition, which is what our current path is on actual existing policies, the emissions embedded in that transition on our current policy path already get us halfway to 1.5 degrees C, our target that we're all hoping for and agreed to at Paris, leaving very little space for the rest of the economy. But the good news is if we increase the ambition and actually get on a 1.5 degree transition path, then the embedded transition emissions are only 5% of the way to 1.5. So I guess that's a 90% reduction in the problem. So the conclusion is that emissions embedded in the transition do pose a complex climate risk that we should be paying attention to. But the good news is that they are avoidable if we get on the right path. Thanks very much.
Thank you very much. And let's move on to the fourth room, modeling hurricane impacts. And here our first speaker is Julia Lockwood.
Sorry, just trying to share my screen. Can you see this?
Yes.
Okay, sorry, just try and make it bigger. Here we go. Yes, I'll quickly introduce our work on 5-year North Atlantic hurricane activity and also US hurricane damage forecasts, which we've produced as part of a Copernicus Climate Change Service project on decadal climate services. So there's a lot of interest in predictions of hurricanes on this time scale, because as you can see from the time series on the right, which is the 5-year rolling mean of hurricane activity, there's very strong decadal variability with this very quiet period in the 70s and 80s, followed by this very active period in the 2000s. So it'd be very useful to be able to predict this variation. And in this work, we use decadal prediction systems, which are basically climate models, but they're just initialized with the current state of the atmosphere and ocean. And these have been shown to have higher skill in predicting North Atlantic hurricanes than traditional uninitialized climate models, which only have the external greenhouse gas and aerosol forcings. And here, rather than tracking the cyclones or hurricanes directly in the models, we calculate a relative sea surface temperature index, and it's the predicted temperature in the main development region of hurricanes minus the temperature of the tropics as a whole, because this is known to be a good predictor of hurricane activity. And then for our hurricane activity forecast, we simply do a linear regression of past hurricane activity onto our index from the model. And this gives us a probabilistic forecast of the ACE index, which is the measure of hurricane activity that we're using. But for the damages in the US, on the other hand, as you can imagine, it's a bit more complicated, because we do find, although we do find a very strong correlation between this index in the model and past observed damages, it's a non-linear relationship. And it's complicated by the fact that there are certain events like hurricanes Andrew and Katrina, whose losses are very big outliers in the time series. And you can see that the peaks they cause in the time series of 5-year loss. And doing full catastrophe modeling was beyond the scope of this project. So we just use a simple stochastic model for the US damages, where we do a log linear regression of the observed past US damages onto our model index. But then we assume that these very extreme events like Andrew and Katrina can occur randomly. And we find that this model seems to have very good skill in both the ACE, the hurricane activity forecast, and the US damage forecast. And you can see that they're freely available on the C3S website here. And I'll be happy to take any questions in the discussion later. Thank you.
Yes, great. Thank you very much. And let's come to the final presentation here. Simona Meiler.
I assume you see my screen.
Yeah, you can see it.
Okay, perfect. Yeah. So welcome to my short introduction on tropical cyclone subhazard impact modeling. My name is Simona Meiler, and I'm a PhD student at ETH Zurich in the Weather and Climate Risk group. And I will not spend too much time, so we can move on to the breakout rooms. But what I basically want to very quickly talk about is how that I model the explicit representation of tropical cyclone wind, rainfall, and surge. In our group, we work with the CLIMADA platform, which integrates hazard, exposure, and vulnerability data to compute impacts. And you've already seen this from Alessio's pitch in the very beginning of this breakout session. The default setup to model tropical cyclone risks is to take a tropical cyclone wind footprint, a 2D wind footprint, and use that as hazard input into this engine. So what you see on the left side is the wind footprint of Typhoon Goni that happened in 2020 in the Western Pacific and made landfall on the Philippines. What I now do is that I also account for torrential rain and storm surges, and analogous to this wind footprint that I just showed, we could imagine running a rainfall algorithm along a tropical cyclone track and then feed that rain into a hydrodynamical model so we can convert the rain to a flood inundation depth. And that's exactly what you see on the left-hand side. This 2-year return period of a flood is more or less the equivalent of a Goni-like storm for the area of metropolitan Manila. When we study a large set of tropical cyclones, we can combine these to perform risk assessment over longer return periods. So on the right-hand side, you see the 100-year event from tropical cyclone flooding. And as I said, this is just a first link of how to extend CLIMADA's default setup. We can add a storm surge, we can add climate change to the whole equation. And if you want to learn more about this, I invite you to the breakout room 4.
Okay, thank you very much, Simona, and all others. Thank you